Okay, the whole process. Let us see the calculations. What is our first token? We just understand it is a token, even though it's a character. Anyhow, we are going to, moving forward with our application, we are going to feed our token. Let us assume this is my first token is represented as my xt, which is represented as a 4x1 vector, one hot representation. So this guy, it is going to be scaled by this weight matrix, input to the hidden weight matrix. Just now we discussed it is a 3x4 weight matrix. So a 3x4 weight matrix with the 4x1 input, the resultant output I will be getting 3x1 vector. So this is the computation I have specified here, 3x4 matrix multiplication with 4x1. So this is the randomly initialized weight. WXH is randomly initialized. For the random initialization, this is the output. What is this? Just your current input xt is scaled by your weight matrix. So this is called as, it's simply net, because still we are not, I should not directly apply activation function to this. I should add my past memory, previous memory, then only I should apply the activation function to this. Okay, this question mark. So this question mark place, what we are supposed to calculate is my previous state memory. My previous state memory is going to come in the form of 3x1 vector. Initially, I don't have any information about my previous state memory, so all are 0. So previous state memory. Of course, if you wanted to add bias, you have to add, you have to initialize the bias also. So how the calculation will go on? So your bias value is 0.567 plus your HT minus 1, which is 3x1, and WHS is represented as a scalar, 1x1 scalar. So between these two guys, your matrix multiplication will perform. So this is 0 multiplied by this, 0 multiplied by this, 0 multiplied by this. With that, you are adding a bias, 0.567. So the resultant, you get a 3x1 matrix operation with 1x1. You got a 3x1 vector again. What is this? This is your past memory scaled by your feedback weight, randomly initialized weight. We yield this. Even I told you, right? Typically, practically, how do we initialize the weight? As the feedback weight is represented as according to the size of the hidden unit. 3x3 also you can initialize. If you initialize this guy as a 3x3 weight, okay, first you should keep WHH first, scaled by your 3x1 HT minus 1. So 3 compatible, so you'll get resultant 3x1 vector. So this is the quantity I should substitute here, isn't it? This is my previous. So 0.56, 0.56, 0.56. You should add these two guys, element wise you need to add. And then I need to apply tan H for this. After applying tan H for this, what is the name we are going to give for this? So far what we have computed? So far we have computed my current state HT, my current state memory, which is HT. Using my present input and my previous state memory, HT minus 1, we calculated the current state. So we just calculate the current state memory. What is my current state output? Whether this memory is good enough to yield the required output or not, I need to verify. So my current state memory HT will be scaled by my output hidden to output weight matrix, which is represented as WHY. What is the size of HT we got? It is a 3x1 vector, right? 3x1 vector. What is the size of my output I wanted to get? 4x1. So to yield a 4x1 size in the output, okay, 4x1 in the output. What is the size of this weight matrix? 4x3, isn't it? 4x3 matrix operation with a 3x1. It is going to yield a 4x1. So this weight matrix I have to initialize as 4x3. 4x3. So let us apply the weight the simplification. Okay, what are the things I need to do? I have to add this fellow to this, and then I have to apply tan H activation to represent HT. Finally, this HT should do a matrix operation with this weight matrix. And then finally, I need to get Y cap after applying the sigmoidal activation function. of course, the softmax activation function. So let us move on to the next step. What is the next step? We have got this, right? What is this? This is as a product of your current state input scaled by WXH weight matrix. What is this guy? Previous state memory, HT minus 1 scaled by WHH weight matrix. Put together, I have added and then I apply hyperbolic tangent to this. So after adding this, I'm applying tan H activation. After applying that, we got HT of size 3 by 1, isn't it? This HT is my current state memory. This guy, we are going to perform matrix operation with 4 by 3, right? So this guy is nothing but the weight matrix connecting the hidden to the output. So after applying the matrix operation between this weight matrix with HT, what is the size I yield the output? 4 by 1. Okay, 4 by 1. For that, I apply softmax to this. After applying the softmax to the output we get, can you see the characteristic of the softmax after applying the softmax to this final stage? What is this? Nothing but this is my y cap of P for the current state input. Okay. For the current state input xt, what we plug in xt, the character h. What do we expect? We expect this is the expected, right? This is the because we need e character in the output. But because initially we started with the random value only, because this is just a first iteration, not even a first iteration, just a feed forward flow. This is just a feed forward flow. In the sequential manner, you are presenting your input. The first node of your output got the highest high probability. I need to compute the log loss, the error I need to compute, and you have to backpropagate the error. Here you are going to backpropagate the error, backpropagated, rolled over the time. Let us understand how this loss is being calculated, how error is being calculated. So error is actually calculated for every time instant. This is I just demonstrated for the one time instant xt. For the given xt, what is the output we got yt? For the whole sequence, I need to compute this loss. So finally, I need to calculate the total loss. Based on the total loss, only your gradient descent will be applied to the overall total loss. First, I'll tell you the individual loss, how we calculate the individual loss. So first of all, you tell me the feed forward flow, the calculation, any part of the calculation, do you have any query? Now we are going to understand how loss is being calculated. So loss is being calculated to the context of what is expected and what is achieved. Okay, this is the predicted probability. What is the expected probability for this here? 0, but the predicted value is very high. What is being expected here? Expected is 100%, but we got very low probability. What is being expected here? Close to 0. What is being expected here? This also close to 0. So we need to minimize these probability. Okay, I need to maximize this probability. So that is the goal of your gradient descent here. So now I'll tell you how this loss is being calculated. First, I'll tell you how the loss is being calculated for every time step and how the total loss is being taken into consideration. So let me represent the RNN unit, okay, like a square block. So my present state, let me give as my first token, okay. So now instead of representing as the xt, I call this my first token at present. My previous state memory, hereafter I'm going to use the notation. Now I'm going to use the literature notation. So from here onwards, let us follow throughout. We are going to follow the similar notations for LSTM, GRU, and everything. So if you look at the paper, the paper published, the biggest breakthrough that happened in the year 2014 and 2015, all the papers related to the feedback architecture came into the application, happened in these 2 years, 2014 and 2015. This is the most happening year for your RNN, LSTM, GRU, all those things. So whatever the notations have used in those papers, literatures, I'm going to use it here. Hereafter, the hidden state I'm going to represent as A, the variable A. Okay. My hidden state, my previous state. If 1 is my current state, I'm going to use 0 is the notation as for the previous state. Okay. So this box is going to yield, okay, this box is going to yield what? A of my current state 1. This is going to yield A of the current state 1. And using that, it is going to yield Y cap of my current state 1. Okay. As soon as it got this Y cap 1, I will have to immediately calculate what is the loss associated with the first token. Because in our previous numerical exercise, we have presented our first token is, of course, it is a character we presented. Okay. What Y cap is produced in the form of a probability score. It is produced a 4 probability score as a 4×1 vector. And that has to be compared with the actual 0, 1, 0, 0. Your log loss calculation is computed and the loss is recorded. We know how to compute, isn't it? For Y actual times log base 2 of this probability you should substitute. And for 1 minus Y actual side, you should substitute 1 minus of this probability score you should substitute. You should sum it over all the 4 values. You can calculate loss for this at this state, loss associated to this state. The same manner, I have to pass, okay, in the same manner, let me say the loss associated to the first token is computed. Next, we are presenting the next token 2. So I call this is A2. Okay, A2. To compute A2, A1 is coming in the feedback. Actually, this is the best way to understand. No, otherwise in the same architecture, I have to overwrite. Instead of overwriting on the same block, we are seeing it's the unfolded version. So unfolded version could be easy to understand. Instead of seeing this like a feedback loop, again, this is being coming. So that is why most of the literatures, if you see, the unfolded version is more popular than the feedback arrow diagram. So now you can see this A, your previous state memory is coming over here. Okay, along with your current input. And we are calculating what is Y cap for the second token. Similarly, you can calculate what is the loss associated to the second token. In the same manner, okay, we can go till the last token. So the last token we represent as generally Tx. Capital T is generally used as a notation to represent the length of your input sequence. Okay, length of the input sequence. So this is Y cap Ty. Okay. So T suffix Y. Again, this loss is represented as so the entire sequence you have presented. If at all your RNN model has to memorize the sequence, this is we have presented this for one time. You have to represent this for multiple times over multiple iterations. So every time what is going to happen? Based on this loss, I have to compute the total loss. 1 to Ty, your total loss is taken into consideration. The same procedure, your loss calculation, your gradient calculation, everything is same. Because this is your softmax. Whenever a softmax is used in the output, it has to be treated as your gradient is calculated as d minus o into 1 minus o calculation. At every instant, you have to calculate this. Okay, instead of every record. Okay, instead of every record, at every time step, you have to calculate that, and you have to take the total loss as the total gradient. So using the total gradient, you know how to calculate how to propagate that. So you have to propagate that error, your gradient value, to update all three weights. Okay, this weight, and of course WHH, and your XH weights. These weights has to be updated. Once these three weights are being updated, once again you represent these three guys again. Represent these three guys over a multiple iterations till the time whatever is being expected in the output. Whenever you present the first token, what is expected, the next token is being expected. Naturally, as the weights are updated in such a way that to minimize these individual losses. So when these individual losses are being reduced, so naturally the overall losses also get reduced. So here we need to consider this back propagation as, but literally physically you cannot see this like as an individual entity. Everything is happened with only one single block. Everything is happening at one single block. Once you presented the entire sequences, your total loss is computed. Okay, this is actually physically only this is available. Once you presented the whole sequences, your total loss is calculated. Based on the total loss, this is updated. This is updated feedback. Actually, this is a feedback loop, right? This is being updated and this is being updated. Then you represent the whole sequences, calculate the total loss, and based on that gradient, you update this, you update this, you update this. So since we are
here, do we also have back propagation here also, or it is just iterative?
Back propagation only we are doing, right? When you take the whatever the what is the gradient I have to use it here. So when you propagate, you have to propagate this delta naught should be scaled by this weight matrix W X Y weight matrix, because delta using this delta naught directly this weight matrix you can adjust, but your feedback and this weight matrix I have to scale this delta naught with W X Y. So naturally it's back propagating, isn't it? It's back propagating to update this weight and to update this weight. So back propagation is happening.
Okay.
So since it is a sequence model, we have to tell that delta naught back propagate, okay, back propagate over time. That is how we should understand back propagate over time. But we're looking at one physical architecture, it looks like at one instant it is happening, but you have fed the entire sequences. Once you fed the entire sequences, you calculate the total loss and you are propagating it back. That means it is equally treated as you have done the back propagation over the time. That is the meaning. Just for your understanding, it is being represented as an unfolded version like this. So to summarize your mathematics involved in your RNN calculations. So hereafter, let us use the standard notation used in the literatures. I'm going to summarize your RNN equations. So how to represent? Let me first give the representation for one unit, one time instant. When I present xt, okay, what are the things are need to be computed? I just give the equation. When xt is being presented as the input, what is the first thing I'm supposed to calculate? What is the first thing I'm supposed to calculate? A of 1, isn't it? This A of 1 is nothing but my current state memory. How do we represent tan h WAA this is my feedback, my past state memory. This is the feedback weight. Okay, the general representation is WHH, we have used it, but I'm using more literature representation. I'm using it here. You can easily understand. I'll tell you what is a logical way you can understand this equation in a logical understanding. WAX x of 1 plus this is the bias attached in calculating the A. So how this notation has been used in the literature is just to indicate. See, this is the weight matrix. This is the weight matrix. Always your first value of your subscription is indicating this weight matrix is going to yield what kind of output. This weight matrix is going to yield a kind of output. We know the A notation is the hidden state. That means this weight matrix is going to yield something it is going to give for the hidden state. That is the representation. The second notation is used to represent what kind of variable this weight matrix is going to get multiplied with. This weight matrix is going to multiply with hidden state. So previous hidden state. So that is the notation convention. Similarly, you can look at this WAX. Once again, this weight matrix is going to yield a kind of output. And which guy it is going to multiply? It is going to multiply X kind of input. What is the X notation? Is the input. So this suffix is called as WAX. Okay, earlier we called this weight matrix as what? W input to hidden. Okay, this is the general notation, but we are replacing this notation as the literature notations. WAX. So hope now it is easy to represent these suffixes. So WAX, because this weight matrix is going to yield a kind of output, it is going to multiply with X kind of input. And this is the bias. This is the bias attached with to yield A. So by B suffix A. So actually, this is the feedback part. Actually, this is the feedback, and this is the current state. Okay, this is your current state. So once you have got this, what I'm supposed to compute y cap of for the current state, isn't it? This is softmax applied over. Can you give the subscription for the weight matrix here? What weight matrix I should use here? W suffix
YA.
Excellent. Because it is going to yield a Y kind of output. This weight matrix is going to multiply with whom? This guy is going to come here, right? So it is going to multiply with a kind of variable. It is going to multiply. So the YA, W suffix YA, it is going to multiply with this. Plus bias attached with the output. So B suffix Y. If you read any literature, you will not intimidated with the equation. Generally, why we avoid literatures? Because we find to understand the equations what we think the equations are too complex to understand. It is nothing. Once you try to understand logically, try to understand the equation, all your equations are given in the literatures, you can easily comprehend. It's not a big deal. These are the equations given in your RNN paper when it is being published in the year 2014. Softmax of this. So I'm going to write this equation generalized representation. So in general, okay, we are going to write this equation in general. You write this as in T notation. Actually, in the paper, they have written in the T notation, but to understand this equation, first I written this equation for one time instead. Okay. So, but in the paper, you can see in general, it is written like this. A of T is the first activation function is represented as G1. G1 is nothing but your activation function. Hyperbolic, typically hyperbolic tangent, or really you can apply of WAA times A of T minus 1 plus WAX X of my current time instant plus bias. Then Y cap T is represented as G2 of W suffix OEA, A current state memory, so AT plus BY. So let us assume my input is represented. Now you are going to tell me the size of each matrix. Okay, as a quick practice. Let us assume the size of my input vector is So far, I have not introduced word embedding. Okay, so let us see the dictionary one-hot encoding itself. The size of each token is represented as 1000 by 1 dictionary. Okay, one-hot representation. Can you tell me what is the size of this weight matrix I should use? Okay, also I'll tell you the size of the hidden neurons you are going to use in this example demonstration is, I need to yield 100 by 1 vector. 100 neurons I'm using in the RNN. Assume that like a dense layer, how do we represent the number of neurons? Here I'm using RNN with 100 units. So the size of AT minus 1, everything will be, or AT minus 1, everything will be 100 by 1. So can you comprehend and tell me what will be the size of WAX matrix?
100 by 1000.
Very good. So 100 by 1000. You can see this 1000 is compatible with this 1000. So it is going to yield, this is going to yield 100 by 1 vector. 100 by 1 vector. So we don't have any idea about this. So we initialize with all zero of size 100 by 1, right? What should be the size of this weight matrix? In the numerical example, I have used 1 by 1, but in the practical, I told you how do we use this? 100 by 100. Got it? 100 by 100 against compatible to yield 100 by 1 vector. So already we got 100 by 1 vector. Here we got another 100 by 1 vector. Element wise, you are going to add. Element wise, you're going to add. And you're applying activation function tan h so that you'll get my current state memory as 100 by 1. Once you got the current state memory as 100 by 1, what will be the size of WIA?
1000 by 100.
1000 by
100.
Thousand.
Correct. So they are compatible. You will get 1000 by 1 because my output size I should get 1000 by 1 because that is the dictionary size, isn't it? So for the given token, what should be the next token is part of the dictionary, isn't it? So which token should get the highest probability? So anyhow, this is a scalar. So we'll get a vector of size for the each value. This scalar will be added. Okay, this is plus by is not a big deal. Similarly here, for each element, it's 100 by 1. Each element, this bias is being added, not an issue. Even after adding this constant, your size will be 100 by 1. Activation function is applied to 100 by 1 to yield 100 by 1. Similarly, for each vector 1000 cross 1 value, your constant is added. Here softmax is applied and to yield 1000 by 1. So when have we able to comprehend the weight matrix? So, but practically how these weight matrix are being even simplified representation. Now I'm going to give a more simplified representation of this equation. Listen very carefully for the next 5 minutes, 5 to 7 minutes. The equivalent representation, whatever this equation, the most compact representation, I can make it like this. A of t, okay, A of t is represented as the activation function. We are applying this activation function. Look at this weight matrix. I can WA, I can make it as a common. Okay, I can take it as a common. So A t minus 1. What A t minus 1? My previous state memory, which is the vector of 100 by 1, can be appended or concatenated with my current representation of my token. Okay, my previous state memory can be concatenated. This is what more practically you should understand the equation in more practical sense. This is the theoretical sense of the equation. Now we are trying to understand the equation in the more practical sense. My previous state A t minus 1, the size is 100 by 1. It is being concatenated with my size of my input. So once this guy is being concatenated, okay, I can use the very common representation of this weight WA. Common weight representation. plus, as usual, plus bias. Now let us try to understand this weight matrix. What is this? This weight matrix also concatenated weight matrix. So the two weight matrix, actually we are trying to represent these two weight matrix. One is 100 by 100 weight matrix, another is 100 by 1000 weight matrix. Now, how I can represent one is a 100 by 100 weight matrix, 100 by 100 columns, isn't it? 100 column weight matrix can be concatenated with, what is the next weight matrix? This weight matrix also 100 rows, isn't it? 100 rows, but 1000 columns, isn't it? So I'm going to concatenate another 1000 values over here. So can you tell me what is the effectively, what is the size of WA effectively? Can you tell me what is the effective size of WA? 100 by 100 by 100 by 1100, isn't it? Am I right? Because you have concatenated 100 columns extra will come, right? So the WA you can concatenate like this is common weight matrix. Now it is going to act as a common weight matrix, 100 by 1100. Now already you have concatenated this fellow, right? How do you concatenate? What is the size of AT minus 1? My previous state memory, 100 by 1. This is being concatenated like this. This is concatenated vertically. And what is the size of my XT? 1000 by 1, right? So what is the overall representation? What is the overall representation of these guys after concatenation? The comma means is concatenation here. Okay, it's comma is the concatenation here. So the overall representation, shall I tell this as 1100, 1100 by 1, 1100 by 1. So this WA effectively it is going to perform matrix multiplication with 1100 by 1. So it's compatible to yield A of T of size 100 by 1. This is more compact representation of the weight matrix. Instead of representing a separate two different weight matrix, we represent this WA 100 by 100 and WA is 100 by 1000. We concatenate like this, and then we do a single operation like this to yield this. Even if you do an individual operation also, you get the same answer. Even if you do an individual operation, but this is a more practical representation of this above equation.
So effectively, there will be just one weight matrix, the back propagation.
Yeah.
Every time.
Yeah. Very good. Excellent. Effectively, it is a one weight matrix. You don't need to operate this back propagation separately for WHH. Separately for WHH, separately for WAH.
Okay.
So one weight matrix effectively can operate. So that is the purpose. So what we have seen, how we present our sequences to our RNN model and how the loss is being calculated and how do we represent this equation. Now we came to the most interesting aspect of how do we represent our input in a more effective manner.